Okay.
So this is for present.
I don't even see the screen, so you need to put it a bit more lightning on. All right. Let me see what else I need. I need to put the voice on. So audio input. Okay, that is on.
It's too bright.
So what I will do is that I'm gonna.
It's better.
Can you check like how healthy is a stream? Is it okay? I hope it is okay. Still, one thing is needed is that we don't see this presentation anywhere here. This is, what is this? Oh, look at that. Cable off. How it look? Is it looking okay?
So let me restart it because right now it's too late.
Okay.
So let me restart.
So it's looking like that. I would like to look a little. So is it? So it's looking like that. I would like to look a little. So is it? With full screen. Okay, let's try this.
By the way, is it attached to that microphone because there are so much noises?
Okay, let's try this. That's true. There's a lot of background noise.
Let's
try this. That's true. There's a lot of background noise. Yeah, it's an echo and everything. Is it because of that that thing that there is that is such a low quality? Because it looked at this guy is okay.
Mm-hmm.
This guy is okay.
What about this OBS?
OBS.
Can you check the selected microphone?
So should I mute this one?
Yes.
I think so. I think it, because otherwise this one needs to be muted too.
Just one.
Yeah, exactly. So now it's just one. This one.
Yes.
Yeah, way better. Way better. Way better. Way better. So only problem to solve is that I need to put this guy on. You know, there is so much technology in my lectures that one can make a doctoral dissertation easily based on these settings, so easily. So, so it's not a big surprise why this is not willing to work. So should I put something here on? Everything is on here.
What about this? Oh no, this is PC.
Is this PC?
Yes. Still.
Oh, now we need to put this on. Still no. By the way, there seems to be a one camera over there. Of course, not for us.
Maybe the rector is watching.
Yeah, rector is checking like what the heck is going on. Wireless? No, now everything is connected. Correct. Everything is well connected, but it's not willing to display here.
So do you want to turn it off and on and off and on?
You mean this one?
No, this one.
No, I think it, because this is there's a green color on. So you were about to click this one.
Yeah.
Is that at too high risk? So this says PC
And it's connected.
and is PC connected. Is there any other cables?
Nope, just that one.
Mm-hmm. Let's try this one more time. How come is this painful?
Can you try this one? The laptop?
Ah, laptop, yeah. So you find another cable.
Yeah.
Okay. Now this is laptop. This guy is on. Yes, it is on. Oh, I think it is in my end, but I think the problem is in my end. Because I don't use computers anymore. I use this Apple Toys. And Apple Toys, the problem is that always when you connected this to another device, you need to get the permission to do that. So I think that I need to go like this. I'm pretty sure that's the problem right now. Let me go this way.
There's no sign of any lights from that project.
Yeah, I know. Audio thing, so I need to reconnect this audio. This audio is back on.
This is not good.
So let's try this one. So for online participants, so we are experiencing some technical difficulties to connect screen to overhead projector. Not the overhead projector, but the projector. It still says nothing.
I still suggest on and off.
On and off.
Yeah.
This guy on and off.
Yeah. Oops. And yep, it starts.
So we're not going to make it. We're going to stay here the rest of the day. Looks promising. And then I'm going to, should I?
Why is it blinking?
Because I think it's warming up. I think there is. What's this?
It doesn't do anything.
Yeah. Right. Okay, let me take a look at what the online participants think this. Okay, so we got 31 online participants, but we don't do well. So we still are not able to put the projector on. And that's, there is a, let me guess, roughly a little less than 100 participants here in the lecture room. Less than 100. And they're unable to see whatever I've. Okay, promising, very promising. This looks good. So bad audio. What about audio? Is it any better? I guess that the audio was problematic.
This one is on.
This one is on. So very, very promising. Almost good to go. Like 10 minutes later. 10 minutes later than expected. Okay, go ahead. Go ahead. Go ahead and go.
Can you reconnect? No, wait a little, still rolling. Still rolling.
But that looks so much better than it was a little while back.
At least we can see a sign of it working.
Yeah, so at least this guy is working. The other projector is not in a good shape. How come he's warming up this long time? So the volume is a little bit low. Oh, it's good now. So it's good now. Okay. But again, we still are unable to connect. So should we? What's this number one?
No, like right now it's working, so we won't touch this. Yeah, because
We need
if
to
it
make it
goes
work
up,
a little better.
it's going to take another 10 minutes.
No, it's not. The voice. Also, the people are complaining about the voice quality. So they're saying that we're going to get back to that as if we are able to put this projector on. Because right now the projector is not willing to cooperate, and that's why the people here in the lecture room, they cannot see these this material, lecture material.
So still no sign. It's still warming up.
How come it's warming up this long time?
I don't think so. So let me try this one.
Okay, so the volume is a little bit more. Okay, no, now I see. I think it is coming. I think it is coming, because this was blinking. This is blinking now. Okay, now we need to click this one. And it's go. Good to go. Yes. Yes. Yes.
Nice.
There it is. So how you feel about this? Was that a big disappointment or what? All right, so we need to go for this, because what happened was that I don't have this USB-C, USB connector that could connect my camera to this system. So we need to go today without the camera. Sorry about that. So the only thing that I need to take a look at is that how this appears. Can you please check, like, if I put this one on? How this appears. Can you please check, like?
Right now the problem is that it's not full screen.
But it's but I think there's a little bit of delay.
Right now.
Yeah, you're still right. Yeah, not. But I think there's a little bit of delay. All right, so I need to. Yeah, you're still right. Yeah, not. Modify this guy. I think that I need to use an entire screen display capture. Right. Can you take a look? How is it now? Can you take a look? How is it now? So it was perfect. Just need to take a camera off.
And can you crop your camera? And
Yeah, I'm gonna take a camera completely off,
okay.
because this camera makes no good today. Yeah, I'm gonna take a camera completely off, because this camera makes no good today. Like this.
Okay.
Like this. Fantastic. Fantastic. Okay. Sorry guys, I see we 15 minutes behind the schedule. Mustafa is going to his bodybuilding session.
So am I going to see you today?
To gym?
Yeah.
No, because I'm no longer going to with you young and beautiful guys. So I go another gym, completely another gym.
Ah, you
Yeah.
changed your gym.
Yeah, more experienced ones.
Okay.
You can say older too if you want. Big respect,
For
guy.
bigger guys.
Big respect, guys, that you're back. I'm very happy to see you again. this is going to be a lot of fun. I can guarantee you this. And why this is going to be a lot of fun? That's simply because subject matter is way more pleasant than it was in first and second period. First and second period was well, if you still remember, it was a partial this, partial that. A lot of partial operations, a lot of mathematics, involving mathematics, no longer the case. Now we're going to discuss about what is that we can do with all the skills we learned in this first class, how we can make a use of practical use of all those skills. And that's what this course is about. There's going to be lectures, there's going to be theoretical lectures. Those are the most boring part of the course, but then there is going to be hands-on exercises that Alfonso will take care of. That's going to be something will be quite a bit of fun for you. And then there's going to be artificial intelligence seminars. That's another something that you're going to learn a lot about different techniques that are currently in use, and that goes under the umbrella of artificial intelligence. Problem in artificial intelligence is, of course, the fact that it covers so many different applications. But because you guys are almost entering the, that out there, you are almost to get your degree, you need to be aware of the technology that is facing you. Because currently the best prediction how the artificial intelligence, large language models and others are affecting your life is that it's not going to be probably taking work out from the engineers. But those engineers that are capable to use AI will replace those ones that I cannot. So you need to be aware of, what are these tools, what is it they can do for you. And the second, let me correct myself, fourth period will be all about AI. So the first, again, let me correct myself, third period will be all about theoretical aspects about computational this and that. And then it's going to be completely different subject matter, artificial intelligence. And I hope that you're going to enjoy a lot about that thing. And I kind of feel that it should be a mandatory course for every single one that are getting the degree from the mechanical engineer, because you need it. You definitely need it. And I hope that your attitude towards artificial intelligence is a positive one. Because right now some people are saying that, yeah, it makes no good, it makes this hallucination and stuff. But that's not the right kind of attitude. It can do a lot of good for you. It can help you, like if you do your Moodle exam using the ChatGPT and other tools, you will score 5 out of 5 automatically. And that's something that you need to use it in a different application, how it can be used to solve the conventional mechanical engineering task. That all you can learn in the fourth period. But anyways, prior to that, we're going to take a look at the picture that I like a lot. This is a picture that is explaining what we do in this course. So we do make a look about the mechanical systems, this one here. So we're going to take a look at how is the mechanisms. And we're not going to touch much of an actuators because we already learned how to model the hydraulic actuators. That's going to be something we're going to left behind. But here in mechanical system, we're going to make a very important extension what we learned, comparing what we learned in the previous class. So we're going to take ourselves from the 2D to 3D. All right, people are saying, okay, this is like trivial. You just add 1 degree of freedom and simple like that. And that's not the case. This extension or this jumping from 2D to 3D is a pretty challenging. And that's simply because the rotations are introducing quite a bit of headache. And what are these headaches and how you can handle those headaches, that we can learn in this class today, maybe the class next week. And that's it. Control system, we are not going to take much of a use of that. We are discussing a little bit about the real-time stuff, but not so much. And then the working processes, that's going to be a lot of discussion about that because of the contact modeling, this and applications different than what we discussed in the previous class. Okay, my name is Aki. Hope you know me already. So I'm the guy that will deliver these theoretical lectures. And then comes Greg. Greg, together with the Sebastian, are the teachers that will take care of the parts related to artificial intelligence. Greg and Sebastian is team taking care of the classes fourth period. Then Alfonso is taking care of the guided tutorials. He's gonna get started next week on Tuesday, if I remember correctly. He's gonna let you know the details via Moodle database. And Mustafa here doing all kind of minor things here and there. setting up the green screen, helping with their gradings and so on and so forth. You met Mustafa already. And then Murica is the one that is taking care of the Moodle database. How is a Moodle, by the way? Is it already open or not yet? Okay, so it might be open later today. The material is kind of ready and waiting for you, but we still need to find the bottom how to make it visible for you. And yeah, I'm sure we're gonna find it out later today. If not today, then early tomorrow. All right, so that's how it goes. What we're gonna do in this class, I already opened that topic a little bit for you, but we're gonna learn to use spatial bodies. I deal with the three-dimensional modeling. Everything in the real life is three-dimensional. So what we learned earlier about this planar case was quite artificial. And now this is gonna be something that is more real life needed skills. And then there's gonna be something that takes a good part of the theoretical lectures, and that's gonna be learn to model deformable bodies, flexible bodies. Now we're going to make a use of the method called finite element method. Are you guys familiar with the finite element method? So your middle name is a finite element method, let me guess. Correct? Yes, his middle name is not that. But what about others? So you know the method, but have you taken any classes about finite element modeling so far? A little bit. And I love the way we communicate here. This is beautiful because I was kind of missing this silence and not to communicate, during the Christmas break. I was because I was with my family members and they talked to me, and it was something that now I'm back in my real life. But again, guys, you can raise a question, you can make a concern anytime you want. But I know it's not going to happen. But if you just shoot it, no need to raise a hand. Just shoot it like, I don't know, okay, is this really the case? Can you make it more real? And then I can try. And you know that I have this bit of the problem that I have every now and then I put a little bit of too much salt and pepper to my stories. And it's your responsibility to see when there's too much salt. You need to say, hey, I don't know, is this really the case? Okay? All right, so understand relation between simulation and reality. This is something that is going to be taking a good part of the lectures. And then to learn critical thinking against computer simulation. Very important. Very important. Because again, remember, we are always in a jeopardy to get something that is called simulation disease. Severe medical condition where there is no remedies, there is no medication against. You need to make sure that you're not getting too much affected by simulation disease. Simulation disease is a brain disease. Goes inside of your brain, delete your common sense, and you are not using your common sense anymore. Even the simplest possible task, you're solving the simplest possible task using a very detailed, extensive computer simulation model. Computer simulation model is to speed up your thinking, speed up your learning. Not more than that. You still need to use your brains. It's not replacing your brains. The same thing holds for artificial intelligence. It speeds up your thinking, but it's not going to replace your brains. Okay. I don't know if AI disease is already a diagnosed medical condition. It might be. It might be because, there are people, I know there are people, and maybe I'm guilty by myself, even the simplest possible task, you ask from the ChatGPT. Another day I was a bit confused about traffic signs. Took a picture from using the ChatGPT and asked, can I park here? And even the ChatGPT is like, is this how little you know about traffic signs? Yeah. So it can happen. So careful with these diseases. All right. Now we're gonna take a look at the different kind of the simulation approaches. This basically based on the Wissing lectures. So we are looking at not just the multibody system dynamics, not just the finite element modeling, but other tools as well. Those are the good picture about the different kind of approaches that are available out there. Understanding the basics of AI technology. Large language models like ChatGPT is this one, surrogate models, data-driven models, AI-based control. These are the subject matters you're going to visit in the fourth period. All right, obtain the overview about modern simulation approaches and applications, vehicle modeling, contact modeling, biomechanics, so on and so forth. Okay, so content, lectures in third period only this period. And then you're gonna leave these lectures behind, and then comes Sebastian and Greg, and they gonna introduce these AI seminars. So they will be organized in a fourth period, and there's gonna be one simulation work. Alfonso is responsible of that. And again, you're gonna get an information about one simulation work a little later. That's probably next week. And this is what this simulation work is about. So it's a simple hydraulic driven crane that you need to introduce a control scheme for it. Okay, so these are the lectures. So we're gonna get started today. So first introducing three-dimensional multibody dynamics, which you are, in some extent, you already know because you are familiar with Euler angles. But Euler angles is a problematic method as it is based on three parameters. And whatever you're using three parameters, you have a different kind of singularity problems, and there's no way avoid it. And we're gonna use a method that is more extensively used in the computer engines, and that's gonna be a method based on four parameters. And you already like, did I make a mistake? Because the body can rotate in 3 different ways. So how come you're using 4 parameters? Well, that I will explain you a little later today. Okay, then flexible multibody system dynamics. So that's going to be first introduction. Then we're going to make a short visit the basics of finite element modeling. So even if you have never heard about finite element modeling, that's fine. That's completely fine because we're going to take a look at the basics. So we're going to take a look at how is the nature of finite element modeling. We're going to focus on displacement-based finite element modeling, which is having its roots in polynomial expansion. So it's not too complicated. So everything is based on polynomials. How these polynomials turn out to be something that is called safe functions, that I will explain here in the very beginning, and how those safe functions are able to create you something that is called stiffness matrix, mass matrix, and so on and so forth. And then we're going to conduct the eigenvalue analysis, because with help of the eigenvalue analysis, different kind, we are able to reduce the model size. So that's going to be something. It's going to take us probably 2 weeks to complete this entire topic of finite element modeling, this one, and then how to conduct an eigenvalue analysis and how to use a model reduction technique in that framework. Jussi Sopanen is introducing the class called, what is Jussi's class called? Machine dynamics. Have you already took the course, or you're going to take it this semester? Right now. Okay, so Jussi is speaking about different space, like one space and another, like how to jump in on different places and how to use this model reduction. So I'm going to support that explanation partially using the multibody framework. Jussi is using this framework in the rotating structures, but we are focusing on multibody applications with the large rotations and large reference translations. So that's a big difference. But still the concept is similar in the sense that we're going to take a look at the different spaces and jumping from one coordinate system to another. And using this jumping one coordinate system to another, eventually we're aiming for reducing the model size. Comes, of course, with the price. And the price is that the accuracy will be compromised. How much that will be compromised, that's something we're going to discuss a little later. Again, still in period number 3. And then bicycle dynamics is our classic visiting lecture. And maybe I'm going to invite myself to make another visiting lecture. We'll see. We're going to figure that out a little later. Contacts, finite fatigue, and other stuff, we're going to somehow squeeze in somewhere here. Okay? How that sounds? Yeah, sounds boring. You're right. But like I said, this was the boring part of the class. Now, there always need to be something sweet, something sour. This is not sweet. This is sour. But then you can enjoy more about this, more pleasant stuff. This is how the life goes. You go to icy water, not because it's so much fun, but because afterwards it feels good. Same here. You go icy water, definitely you are not going to enjoy when I'm explaining about these subject matters about finite element modeling as such to you, but then later everything feels more pleasant. Makes sense. So easy life is not the good life. We learned that. Hard life, good life. I don't know. Too philosophical, because we still, good to keep in mind that we're in the mechanical engineers. So we're in a department of mechanical engineering. We don't do this kind of heavy thinking. Okay, so the seminars are getting started in week 10. Information will be announced by Sebastian and Greg. Mainly, I think that Sebastian is the one that is responsible of this particular part of the class. Maybe Sebastian has already listened to this, don't know. But anyways, he will get back to you with these details. Right, so these are tutorials. So it's a little bit of 3D modeling, hydraulic modeling, flexible body modeling, verification control algorithms, and robotics. And grading, this is something that you need to be aware of. Extremely important. Okay, you can get 1/3 of the grade based on the simulation work. This is Alfonso's responsibility. AI workshop, Greg and Sebastian. Another 1/3. Written examination, which you need to take a look at my lectures. That is worth of 1/3 of it. And the final grade will be computed as follows. So it's going to be simulation work added by written examination, added by AI workshop, divided by 3, added by in-class quizzes. Now, this is how you can get the points from different kind of the tasks. So written exam from 0 to 5, simulation works from 0 to 5, AI workshop from 0 to 5, in-class quizzes 0 to 1. Okay, so let's make an example here. So you're going to get 3 out of simulation, simulation work. So that was 3. And then you're going to get written exam, that's going to be 4. And then you're going to get one other 3 from, what is it? This was a missing AI workshop. So that's a total of 10 divided by 3. It's going to be 3, 1/3. So what's going to be your grade? Not necessarily, because one missing component, in-class quizzes. Where is it? This one here. So if you're going to get 1 extra point from that, so it's going to give you 4. Simple like this. There is a, well, we're going to take a look at the in-class quizzes options momentarily, but this is how it goes. Keep in mind this, because in theory, this is possible too. How can I kind of forget like how to use this? Oh, here. This is possible too. You get 5, 5, 5, 15 divided by 3. It's going to be 5, added 1. 6. I cannot give you 6. I would love to do it, but and I tried this earlier, but student affairs office is not happy when I send, okay, this guy is scoring 6 out of 5 this class. They're like, okay, this is not fun. This is not cool. So the 5 is max. Okay, another responsibility. So far you have one responsibility, that was to make sure that I'm not putting too much salt in my stories. Okay, deal. Another one is that you need to use a most effective concept of mechanical engineering, minimum energy principle, when you're scoring out of this class. So do the math. Don't do too much work. Optimize. Use a concept called minimum energy principle. Use as little energy as possible to get the highest possible grade. Can you do the math? Good. Sounds good. Sounds good. So if you're scoring 6 out of 5, maybe I should penalize you and give you a final grade to be lower than 5. Well, I don't do that. But again, this is if you're going to score 6 out of 5, for sure you're not following the principle of minimum energy. Okay. All right. So tutorials, like I mentioned. By the way, so the lectures are actually on Mondays. Don't know why they are this time of the day this week. That's a little bit unclear to me. Maybe because the Monday was a holiday, or not holiday, but university was closed. Anyway, so getting started next week. All the lectures are on Mondays from 10 to noon. And the lecture room was not mentioned here, but it was something like 7335, if I remember correctly. So not this class. Thanks God, because this class obviously is not a very good place to be. All right. Not mandatory to participate in any of these classes. What else? Yeah, okay, this is not clearly mentioned here. I think I need to send you an email. But we're expecting each of these components to be successfully completed. So even if you wanted to score the lowest possible grade, we're expecting you to participate in the written exam and score at least 1 out of 5. Same holds for AI workshops, so you cannot just skip it. You cannot. And try to make sure that each one of them are successfully completed. Successfully will be that you need to score 1 out of 5. So 1 out of 5 will be the minimum. All right. Okay, so that's the way to go. In-class quizzes, 20 points. Business as usual, so this is not anything too complicated. You know how to deal with that. So you guys all took a class, simulation of mechatronic machine. Phone is ringing. Gonna take this phone call right now. You all took a class, simulation of mechatronic machine. So every single one of you.
No, I'm an exchange student, so I arrived.
Oh, okay. All right. What about others? So you're the only one. Okay, so this is going to be a little bit of rocky road to you. And why is going to be a rocky road? Because explanations related to these flexible bodies, or let's say this beginning of when we get started, it is related to multibody system dynamics. And these guys, others, they are very much knowledge about this subject matter, which you don't have no idea whatsoever. So you just hang around. It's going to be fine.
But I did similar courses in my home institution.
Oh, nice. So what's your home university then?
It's IMT Atlantic in France.
Okay, all right. Yeah, I'm not aware of this class, but that home university, your home university. But anyway, so you know all about multibody system dynamics. Some knowledge. Okay, I think it is good. Good enough. All right, so this was only related to simulation work, so all midterm reports must be submitted successfully. This is for your sake, because if we say, okay, just submitted the final report, it's going to make your end of the 4th period to be miserable. So that's why we're expecting you to do this in a timely manner. And if not, we're going to penalize you a little bit. So if you miss the midterm deadline, we're going to take 0.5 points out of the maximum grade. And if you miss the final deadline, fine. We're going to just divide your grade by 2. You can do the math. So even if you do the best possible work, you are not going to score very high if you miss the deadline. So don't miss it. So it's important to be on time. So these are the deadlines again, but again, the details will be offered by Alfonso. Previous attitude. What we need as a previous knowledge is a can-do attitude. So you're okay if you hold a can-do attitude. So that we all know this because we learned this in simulation of mechatronic machines. So we learned that we can make things to happen. So we can learn something that is extremely challenging, that is all about partial this, partial that, matrix this, matrix that. And that was an attitude game. And you learn it. There are other materials. So there's a PowerPoint presentation, other material that is available in the Moodle database as soon as it's opened for you. And I hope, again, today, tomorrow latest. There is this Ahmed Shabana's book, which I recommend you not to read, because it's made for doctoral students and you are not yet there, so you're still a master level student. So that book is a little too heavy in my mind. You can borrow it from the library if you want, but honestly, not for you guys. So it's a little too heavy. But I'm saying Ahmed Shabana because he's my supervisor, and of course I need to marketing his book a little bit. And the educationally is okay book for doctoral students, not so much for master level students. All right. Let me take a look. Should we go this introduction and then have a break, short one? And then I think we're gonna leave then sometimes, hopefully a little earlier than 6 o'clock, because it's getting late. It's kind of getting late. And this, the class on Monday is not going to be after 4 o'clock. It's going to be, like I mentioned earlier, at 10 o'clock. And I have no power to change the time. I know that now this is inconvenient time for those ones that are not physically here, because you might be working and you might not be able to follow the streaming, which is a little bit of problematic, because then you cannot enter the answers in in-class quizzes. But I have no power to change the timing. So this timing comes from the Student Affairs Office, and whatever they say, I have to obey. I have not enough power to change the timing, so I just cannot. So don't send me an email and ask, like, can I change the timing? Because I cannot. I cannot. All right, so what I will learn in this course, so this is a short explanation. Oh, look at that. So a little bit about the different tools, a little bit about the multibody system dynamics, finite modeling, a little bit about the hydraulics. This, by the way, may be something that you are not familiar with, because the hydraulic modeling is, I don't know if they explain that too in your home university. Anyway, so there is a supplementary material that helps you to conduct the modeling of hydraulics, control algorithms, a little bit about the CAD software, a little bit about the context, and so on and so forth. So basically combining multiple different software in one package. That's what we're aiming for. And we also take a look at, how is that we can model rigid bodies that are assumed to be rigid, because there in real life there's no such thing like rigid bodies. But, we can sometimes assume to be models, bodies to be rigid enough that the flexibility doesn't affect much to the final responses. And now we're going to model the flexibility using the method that is called floating frame reference formulation. And I'm hoping you know after my class where this name, floating frame, is coming from. That's at least the minimum amount of information I'm hoping you to adapt. And then maybe something about large deformation cases too. Probably we are not going to spend too much time about that. Here's an example about flexible bodies. This particular animation shows you how is that cables can be modeled as flexible bodies. Okay. Right, so they are not based on the floating reference formulation, but we can shortly look at another formulations too, just to give you a nice overview. All right. So moving forward, then we're going to look a little bit about the fatigue. Another subject matter, or one subject matter that I believe that is fairly popular in students in mechanical engineering is steel structures and welding. So are you guys taking any classes from the specialization of steel structures? So you take some. So one of the subject matter that they are specialized to is a fatigue. And we're going to touch the fatigue, but a little bit of different point of view than the specialization of steel structures, because steel structures, they are really deep into the fatigue. And they can make a fatigue-like prediction once they know the kind of like stress history. And we are showing that, I'm going to show you how you can get the stress history based on the flexible multibody system dynamics. And we're going to focus on welded structures. And here's just a good example. This is a hydraulically driven crane, lock crane, where there's welded knot here for just to hold these hydraulic pipes. And whatever you use in welding, you need to be aware that the welding is dangerous in terms of fatigue, because welding always introduces high residual stresses. They're going to be roughly the amount of yield stress locally, very, very locally. And then there's another big problem related to welding, and that's the fact that welding process itself will introduce defects somewhere in a welded toy, somewhere here. And these defects act like an initial crack. Now we have two dangerous components, high residual stresses, initial crack. Combination of these two will make welded structures to be very vulnerable for fatigue. And you can learn how you can predict the remaining fatigue life using the technique explained in steel structures. But I'm going to explain you how you can get the stress history. Okay, so that's something. So careful with the welding, because welding always a problematic in terms of fatigue. Right. So then a little bit about the contact modeling. So we're going to take a look at, there's supposed to be an animation. Is it running? No. Cannot make it this run. Contacts that are related to ball bearing modeling, and other stuff. Also related to a little bit about the game technology, because in games the contacts are extremely important. You're going to learn the technique that is called many-body dynamics. You know, we have multi-body system dynamics, and then we have a many-body system dynamics. What's the difference? Well, the number of bodies, of course. And where is the limit when things turn out to be from multi-body to many-body? It's not actually based on the number of bodies itself, but it's based on how the contacts are modeled. And basically, contacts, just for your information this time, there's a smooth and non-smooth dynamics. Smooth dynamics will be based on the body penetration. So if you have like a ball that is coming to the gravity to this kind of a surface, so at some point what's going to happen is that ball is going to be here, and this is going to be the area that is penetrating the surface. And now you can compute the force that is pushing off this ball using this penetrated area, or amount of penetration. This is smooth dynamics. You can do the same by using inequalities, complementary theory, where you are saying that, okay, the ball can do anything it wants, but it cannot penetrate. Now this is going to be the constraint. It's a little bit similar than the constraints related to joints, but conceptually a little different. And then ball can come be here and then bounce back. That's non-smooth dynamics. Conceptually different story. Right. Now, that's it. Now, here's what I propose to you guys. So we are ready to jump into the 3D multi-body dynamics. And here's my deal to you. Like, there's going to be, the motivation you to follow me is to do well in a written exam. Correct. There's no other reason to be here. Correct. Okay. So how is that we can optimize? Again, using this concept called minimum energy principle. This is the way to go. I'm going to tell you all the questions that I can ask from each of the subject matters. These are the questions that I can ask from this subject matter. There's a total of 11 questions. We're going to cover each of these questions. You can look at these recordings later in YouTube. You're just practicing these questions only, and mastering these questions, you're going to score really well in the exam, written exam. Make your life more pleasant. Here's what I offer to you. So there's going to be a voting action once we're ready to step into the exam. And in this voting, you can select the one question that you hate the most, that you really hated. And if you select the question that you hated the most, that question will not be in a question bank. And if you can make another selection, you can select the question that you like the most. That question, for 100% certainty, will be in your exam paper. How that sounds? It's based on democracy. So it's not going to be individual cases, but we're going to set the voting actions, and based on democracy, 2 questions. That one will be in the exam paper and one will not be there. Rest will be randomized. Deal. Okay, are you coming back next week, Monday, to follow these questions? Yeah, now you say, yeah, but we'll see that. We'll see that. Okay, break. Let's take a break, and then we're going to discuss about 3D multi-body system dynamics. And we're going to get started. Simple things. What kind of system can be analyzed using multi-body system dynamics? What couple simulation means? Okay, so that's something that I need to explain a little later, not today. Why rotation, oh my God, this is unclear language. Why rotation are more difficult in spatial than planar case. R is missing in my question. Okay, I need to go and get coffee. Is it 5 minutes enough? 5 minutes. Okay. Next time, I remember I need to take more stickers with me because we have plenty of these stickers related to mechanical engineering. A lot of different kind of fun stuff. I don't have it with me today, but next week, Monday. Mikäs tää on?
Sellainen älykäs YouTube-kommentti.
Missä? Tästä kurssista?
Ei tästä kurssista löytyy.
Tuossa kun ei saanut sitä YouTube-kommenttia, kun toi on toi päällä, niin ei tiedä, kun ei se
Anonyymi. Joku levitti saippuaa miesten pesutuolilla Lappeenrannan uimahallissa. Kaupunki laittoi hallin saippuat pannaan. Se selittää niillä, että on muuttamassa ja näin. Mä en tiedä ymmärtää. Toivottavasti ne ymmärsi.
Oli vähän epäystävä, kun toi kotirahoituksen muuttuminen oli tosi petollisen helpolta, että ehkä jotain tajuamatta silloin kysyttiin minne ja paljon neliö ja turvalähteitä eikä mitään muuta, mitään hinnan muuttumisia tai mitään.
Semmoinen klassikko juoni. Kaikki rahat sinne pois. Tonni 600 eurosta.
Sitten kyllä pitää alkaa rikkomaan jotain sehän aika totaalisesti vuokrat. Jääkaapin termosta. Useasti 400 jotain välillä häkyrissä nousee siellä.
Mulle tää varmaan maksaa niinku saman verran kuin aikaisemmin. Okei. Niin missi sitten se meni. Kato kun
Onks tuossa
mullahan
pörssikäynti vaikuttaa?
niin kato kun mulla on justiin se vuokravaistu periaatteessa. Niin mä ymmärsin, että noin jutut muuttuu jotenkin, mutta ilmeisesti se on käyttänyt saman määrän rahaa kuin tähän sanotaan. Hintatulisen tarkistus alkaen. Tässä on tarkoitus olla muuttunut asumismenot ovat noin paljon kuukaudessa. Asumislisän määrä on tontara asumismenoille. Joo. Asuntosi sijaintikunta on joo. Hyvä. Aha. Onko tää vielä? Niin, mä tein osoitteen muutosta. On ja sen tein.
Jaa.
No, joka tapauksessa me
Lasket.
Ilmoituspiste.fi. Eiks mä pitänyt?
Jos vaihtaa sinä sitten näköisesti digigrafiikoita, niin
Oman mielestäni.
Mutta ei sitä oikein tarvitse muualle vaihtaa, kun ne saa automaattisesti
Niin, ne saa
sen
kaiken.
yhteen paikkaan.
Niin sitä mietin ihmettelen tässä. Palvelukontrolla sitten. Joo. Me kyllä on laittanut sen, että me on muuttanut osoitteen. No, se on minkä pitää tehdä uusiksi vielä. Ei.
onko teillä posti?
Siis tämä posti sanoo, että tämä on minun osoitteeni.
Se
Siis me ei katso täältä, että me ei yritä muokata sen. Se on se uusi.
Joo.
Niin emme voi tehdä sitä. Se tietää, että mun osoite on vaihtunut. Mutta jos me menen sinne digi- ja väestörekisteriin, niin siellä se sanoo, että se on korporaatio.
Eikö se nimenomaan pitää sinne digi- ja väestöön?
Eikö tossa kun vaihtaa, niin se vaihtaa molempia. Se sanoo posti ja DVV molemmat vaihtaa.
Ainakin joku viikko.
No, siis
Tai milloin se tiedät?
on sit jo aika. Osoite.
Onko teillä postitusta vastaan? Kertaa.
On, mutta mulla on posti. Mulla on se vanhan, tai siis sen hyvä suhteen se korporaatio, jos se nyt tulee mun postiin.
So the cafeteria was actually closed. So I just have to go all the way to Les Lounge. That's why it took a little longer than I anticipated. Okay, so let me just check that the streaming is still healthy and everything is fine. Where is this? There's a YouTube. No, somebody's just subscribed my channel. Here. And it looks good. Looks good. Okay, so what we're gonna do next is we're gonna just refresh the mind about what is a deal with the multibody system dynamics, and then comes the actual extension to 3D, which, like I mentioned earlier, is something that you are partially aware of, because you know the technique that is based on rotation method that is based on 3 parameters. But in real life, these 3 parameters are not used, and that's simply because of the singularity problems. There are more advanced techniques that are available, and we're going to take a look at those most advanced techniques, and this is where we're going to end today's lecture. So we are not going to go any further than that. So I'm expecting some half an hour or so, and then you guys are good to go. And that's simply because I was the one that was messing with these technical difficulties, not you. So it's not right to penalize you because of my unexperience about technical things here. But let me ask you this, because there's quite a bit of headache because of the YouTube. So you guys have valued the YouTube, or would it be better to use another streaming tools like Teams or something more conventional? It doesn't really matter. Doesn't matter. Doesn't matter. Okay. Yeah, that's kind of hurt my heart because I really are putting a lot of effort to try to make things looking good in the YouTube. But maybe you're right, doesn't really matter. The only positive thing about YouTube, I understand that the YouTube is good in the sense that in my end everything happens automatically, and people not participating in this class, they can take a look at this content if they want. Usually they don't want. But the problem is that it comes with commercials that could be a little bit annoying every now and then. And I don't know, which one you prefer? Is it making any difference, or does, if you have to select, which one you would select?
For Teams, there's a transcribe, so you can just get the minutes or like the whole lecture minutes.
Okay, so that's something that you feel that is a useful thing to do. So you but can you get the same in a YouTube? Probably not. But in a YouTube you can use closed capturing. Can you do the same in Teams? Have you ever used it? Because you can switch this to any language you want. So that I feel that is pretty useful because it's quite accurate. It makes mistakes here and there, but not much. So okay, so this class will be still in the YouTube, but I need to think what to do next semester, next academic year. So should I actually go back to, I don't know. Okay, there. I need to have a break, another 1 minute break here because I need to make another phone call just shortly, and then I will be back with you. Sorry about that. So it's a hard start for today. Just a second. Just a second.
Aika vaistentissä kysytään, mikä prossu on omassa koneessa. Minkälaisessa löytyy sähkö, joku sähköteltta. Kyllä mukava. Joku sähkörakka. Niin, siitä kysytään, että mikä prossu on
So I'm really a multi-purpose guy because I'm handling so many things simultaneously. So this was a domestic problem that I fixed. Now back in 3D multibody system dynamics. All right. Okay. What's up with the multibody system dynamics? Like the title implies, this is a method that you can use to analyze systems that consist of multiple bodies connected together via joints. The joints are kind of the component needed. So if no joints, there are better methods available. Another thing that is extremely important, that we do not make any assumption whatsoever regarding the magnitude of rotation. And that's something that is a fantastic. Example that I used you earlier was the pendulum. You know, pendulum, if you look at your notes about Dynamics 1 and Dynamics 2 from your bachelor level courses, you typically make an assumption about small rotations. Rotations, let's say plus, minus 10 degrees, sometimes even less than that. This is where you can linearize things and you can find sometimes even analytical solutions for cases like pendulum. When you have a large rotation, like this much, you cannot. This becomes to be a nonlinear system, and you have to use sine and cosine trigonometric functions to describe its kinematics. And when that's the case, there is no analytical solutions available. What you need to do is that you need to create the equations of motion, solve those equations of motion in forward of time, and that's the way to understand the performance of systems. Okay, so it's pretty straightforward approach, just based on the few steps, and you can automatically, more or less automatically create the equations of motion, and it can be used to analyze robotics, mechanism, vehicles, many other things, biomechanics too. bicycle dynamics if you want, if that's what you want. Okay, it is, there's many different ways how you can describe the kinematics. And kinematics is actually the only decision, or how to describe the kinematics is only decision you need to do. Rest is just following the methods of physics, theory of physics. But the kinematics is a choice of how to describe the bodies in 2- and 3-dimensional space. In a previous class, we learned that one of the efficient method is based on body reference coordinate system. The body reference coordinate system that is attached to the body. It translates and rotates along the body, and it helps to describe the particles within the body. This body reference system can be located anywhere at once within the boundaries of the body, or even outside of the boundaries of the body. Doesn't make any difference. Beauty is this: particles with respect to this body reference system remains constant. The location remains constant. So if I describe the particles within the boundaries of the body using the vector u bar, the vector u bar is constant. So it's not the function of time. And that somewhat simplifies the description of kinematics. So the components you need are vector r, that describes where the body reference coordinate system is located at with respect to global coordinate system. And then you need to know what's an orientation of body reference coordinate system using rotation matrix A, and then the vector u bar. Those are all the components you need. So explaining these together with the vector r looks like this. This is a kinematics. In 3-dimensional space, this component consists of 3 components that are along the global coordinate axis. And this is a 3x3 matrix that is based on 3 parameters or 4 parameters. Still, dimensions are all the time same, so it's going to be 3x3 matrix. This guy here is a vector of 3 components, like this. Nothing new, pretty simple. Okay, now all right. Then there's a written explanation of why life is so difficult in a 3-dimensional space, and I guarantee you don't understand this. But if you have a little bit of understanding end of the next week lecture why this is difficult, I will be so proud of you, a little bit proud of myself too. But basically what this says, why this is a difficult business here, is simply because a vector of angular velocity vector is not the same than time derivatives of generalized coordinates. This needs to be explained. Okay. Angular velocity vector that describes the angular velocity with respect to global coordinate axis or body reference coordinate axis. So there are 2 alternatives. Could be, these are the alternatives. These are not the same than, this vector here, this 3x3 vector is based on 3 parameters or 4 parameters that can be called let's call it θ1, θ2, θ3. These are never same than this. Let me call this as a vector, theta vector. These are not the same than this one. This is not the dot. So not supposed to be not the dot. This is always different. Yeah, I know this sounds like not the same, but this is something that is actually very fundamental. We're going to take a look at this a little later, and if you understand why they are not the same, that's going to be a big jackpot. But there is no method currently that can set these 3 parameters to be same than angular velocities in global or body reference coordinate system. But again, this time for your information. Next week, more about details. Why this is the case, and why this is something that makes life in a 3-dimensional space a little complicated, and what's the remedy to fix this problem. There's a remedy to do that, and we will get back to that a little later. All right, so that's about why this is so complicated. Description of particles, and we're going to use this technique that I just explained to you, so we're going to use a vector r, a combination of rotation matrix and vector u bar. And again, this is some people don't like to use this method because this method is called like a method based on global coordinates. There are alternatives. Alternatives are method based on relative coordinates, where you make a use of the structure of your mechanism. Like, just to give you an example, 4-bar mechanism look like this. Like this. And how we're going to model this 4-bar mechanism is that we're going to take a use of, we're going to model each of these bodies using these global coordinates. And these global coordinates are this guy here and this guy here for every single body in my 4-bar mechanism. Like this. Like this. I could alternatively use a completely different method where I'm just describing what is a body orientation with respect to a body before. And if this body here is called like a body 1, then the only coordinates that I need to know is the relative coordinates between this body and the global coordinate system. Between the body 1 and body 2, this is called body 2. I only need to know their relative orientation. This relative orientation can be automatically used as a parameters to describe the equations of motion. And this is completely different method, and it's called method based on topology, system topology. And this is leads to the minimum number of differential equations. But what we have learned is a method based on global coordinates. It can lead to minimum number or maximum number or somewhere between these two extremes. But the beauty of this method is that this global method that is fairly straightforward to use. Of course, comes with certain complications, but it can treat with a different kind of mechanism, mainly in the same matter. Okay, this is for your information. We might visit this a little later, but this time for your information. Euler angles. And again, any comments, by the way, this time? Pretty clear. Anything you want to ask? So it's clear. Yeah, I got the new, by the way, we got another level of communication because earlier it was like this and this and this. This was this confused, but now I learned another one. This is like, but I don't know what that means. I'm a little bit confused. Like, what is this? Is it like, go ahead and continue? Oh, this is go ahead and continue, right? Go ahead and continue. Okay, which one is that? So can you give me a sign what to do next? Oh my God, I got another one, like this one. This is go home, Aki, go home. Okay, all right. Euler angles. So we're gonna go all the way out Euler angles, Rodriguez equation, and Euler parameters, and that's where we're gonna end today. So I'm not gonna go further than that. So Euler angles, business that you know. Explain the concept of Euler angles. Explain the gimbal locking. Locking, which is not mechanical lock, but inability to describe rotations, because these three parameters they can be singular. All right, so Euler angles is something that we learned in the last class, so I'm not going to go details this time. So it's based on 3 successive rotations. Successive means one rotation after another. So rotations in line. So first rotation will take, this is the most commonly used sequence. There are other sequences available too, but often used sequence is that the first, you set 2 coordinate system to be completely parallel with respect to each other. Then you take a hold of the z coordinate axis. You introduce an amount of rotation that is called psi, whatever. This one here, what is this? Psi, I just don't remember this. Psi. Yeah, that's what I said. That's what I said in the beginning. Phi. Yeah, phi. This is phi. Like this. Phi. Okay, so you introduce amount of rotation that is phi. All right? So then you have once rotated coordinate system. You're going to take a hold of once rotated coordinate system, and you're going to introduce another rotation, this time around x coordinate axis. You're going to introduce a rotation amount of theta. That I know. That's theta. And then you have twice rotated coordinate system. You take a hold of, again, about z coordinate axis, and you can introduce amount of rotation that is phi, psi, phi. What the heck is this? P. So, whatever, okay, we don't need to pronounce this complicated word here. So it's just the amount of rotation called, yeah. But it doesn't really matter. I think you know what it is. You know it better than I do. Okay, but now the bottom line is this. Now we have 3 rotations, and we can describe each of these rotations by using 3x3 rotation matrix. And always in 3-dimensional space, successive rotations can be obtained by multiplying rotation matrices together. Multiplying order makes quite a bit of difference. So you need to be careful not to change the order, because otherwise you miss things pretty significantly. But again, people are asking like where this is coming from, and I think it is coming from gyro. In gyro, this is a z coordinate axis, this is x coordinate axis, this is again z coordinate axis. Maybe this is an explanation. But again, here you see already that the problem you have, whatever using 3 parameters, because what can happen is this. This third axis can become parallel with the first coordinate axis. When that's the case, then you cannot recognize if the rotation will be based on first or a third rotation parameter. This is inability to recognize what is what. So you cannot just recognize, which one is the correct parameter to use, because there is no correct parameter to use. It can be 2 parameters instead of 1. So this is called Kimball locking, which is inability to describe rotations in certain configuration. It can be pretty dangerous, and there are ways to avoid it mathematically. I don't know how they are avoiding that in the gyros, but this is something that is always a problem when using 3 parameters. And then many are saying that, hey, I know the solution for that. So we just use a different rotation sequence, and that's a simple fix. No help whatsoever, because even if you change the rotation sequence, you can always put your system in a way that 2 coordinate axes becomes to be parallel. And when that's the case, then you're losing the ability to recognize what is what. That's the one that is called Kimball locking. So not the mechanical lock, but inability to understand what is what. That's what it is. All right, so like I said, in a 3-dimensional space, you can have these rotation matrix describing each of these 3 rotations. And this is something that looks very much familiar with us, because these submatrices are coming from planar cases. Simple thing. And these are the ones that is showing how the rotation takes place. This is z, this is x, this is z. Once you multiply these together, this is how the rotation matrix eventually look like, based on 3 parameters. And again, this is the concept behind. And this is how it looks in details. This is a little bit about what I just explained about the Kimball locking. There are really nice videos about the Kimball locking, which I recommend you to take a look. So you can, I cannot click these, no I cannot. Cannot click these videos. I cannot show this one here either, but I'm going to put these links to the Moodle database. So click these links and take a look. Then there's a really nice explanation how this was dangerous in an aerospace application, and it was explained by this lady. Again, I cannot play this to you today, but anyways, take a look at it and enjoy, because this is pretty practical and pretty enjoyable to watch. All right, my first in-class quiz to you, and the business as usual in-class quizzes. Please lock yourself to Socrates and answer this question. I need to modify this. It's not yet on, but I'm going to put it on momentarily. Okay, so and I'm going to explain what's the first in-class quiz. Teacher's Pat. All right. Yeah, this is too small, so you cannot see this well, but let me show it to you here. So when using three rotational parameters, a problem is singularity, physical interpretation of parameters, meaning that you don't know what is, how they are related to reality. And then the last option is that the usage of three parameters is limited to small rotations only, meaning that you can only describe this pendulum we described in the very beginning. One only option is correct, but which one is correct? Yeah, I feel the same. Yep. No, not this one. This one. No, something is off. I know what, by the way, I know what the heck is off here. Because oh god damn it, this is not the best day to me. Because at first I forget this adapter to connect my camera to this computer. And now I know this class here that I'm using is incorrect, because you can only log in if you've been enrolled to the simulation of mechatronic machine. So our visitor cannot log in. You cannot log in.
I'm trying to.
Yeah, but you will not be able to do so. So what's going to happen is that, again, because of my, because I want to be too clever with this technical stuff, I'm going to give you full points for each one of you. But let me take a look, because I got 27 answers, 28 answers. So what's the correct answer? A, that is correct. So that's the correct answer. Let me just see how the people are answering. Not great, because this physical interpretation of parameters is not correct, because each one of these parameters are telling what is a rotation and how the rotation takes place. So there is a clear physical interpretation behind. Usage of three parameters is limited to small rotations only. Very much incorrect, because particularly when you look at this, take a look at this. So whatever you see, sine, cosine, is a clear indication to you that you are dealing with nonlinear dynamics. The most common source for nonlinear is large rotations, because large rotations you cannot describe anywhere. I mean, the most common way to describe it is to use trigonometric functions, sine and cosine. These guys are not linear component, but they are nonlinear component. Okay? So lesson learned. So whatever you see, cosine, sine, you deal with the nonlinear dynamics. So why you need to deal with the nonlinear dynamics? Because of the large rotations, or not the nonlinearity. But most common source of nonlinearity is large rotations. You just cannot describe this guy easily without using this cosine and sine. Yeah, I'm saying easily because there is a technique, but it's so complicated to use that we are not going to touch that. So there are techniques that are based on translations only, but eventually they're going to be nonlinear too. So let's just conclude that whatever using cosine, sine, trigonometric functions, you deal with their large rotations. Okay, makes sense. Makes sense. All right, so moving forward. So this was a method based on three parameters. And because of the three parameters, we have this problem of singularity. That's the problem. Inability to describe the rotation. So sometimes two rotations axes can be parallel. And when that happens, then you have this singularity problem. Rodriguez equation. Two more subject matters and then we will be out. The Rodriguez equation is a little bit painful, needs some thoughts. And then the Euler parameters, which is name-wise very close to the Euler angles, is concept that is based on Rodriguez equation. It's just a name game. So we're just calling the parameters introduced in a Rodriguez equation differently. And we're going to get Euler parameters. And again, Euler parameters, Euler angles, they're a different story, completely different story. This one here is based on three parameters. This one here is based on 4 parameters. Name-wise, it looked like they are cousins, but they are remote relatives, very remote relatives. Okay, Rodriguez equations. These are the questions. Explain the concept of Rodriguez equations. We're going to take a look at the Rodriguez equations next. Explain the concept of Euler parameters. This is a name game. We're going to take a look at that too. In three-dimensional case, a body orientation can be defined using Euler angles and Euler parameters. Explain the concepts of both methods and how these methods are different. And again, we're going to touch this next week in details. But we're going to get started with this guy, Rodriguez equation. And to make that happen, we need to set the two vectors. I need to get some kind of another vector. So I only have one vector in my hand, but I need another one. I'm going to take another one here. Okay. So a Rodriguez equation goes like this. You take a vector, random vector. This can be any length you want. This is in having the random orientation in the space. You take and rotate this vector another orientation in the space. When you're comparing this original configuration and the final configuration, this is how you can compute the Rodriguez equation. To make things to happen, you need to get an assistant vector, because otherwise you just cannot make this miracle to happen. This assisting vector is the one that you will attach to the origin of your original vector, like this one. And then you introduce in the rotation by taking a hold of this newly added vector and introducing the amount of rotation that is called here amount of theta. Now, this is how things are going to happen. So let me explain again. So you have a vector in random orientation in a space. You can put this vector in another orientation in a space, and you can make it happen with your assisting vector. This is your assistant here, and your assistant you can attach to the origin of the original vector like this. And then you can introduce the rotation by taking a hold of your assisting vector and introducing amount of rotation that is called theta. That's it. Now the only thing you need to do is that you need to create a mathematical relation between the original and final configuration with help of this assisting guy. There's a trick in this assisting guy, and this trick about the assisting guy is that this assisting vector is unit in a length. So it cannot be random in a lengthwise. This can be any length you want, but this assisting one is unit in a length. Unit in a length, whereas another example about unit length vector, well, the coordinate axis is a unit length vector. Okay? So two guys, like the real guy that you want to do the introduction, you want to introduce a rotation, and then the assisting guy. Okay, now here's a configuration. This is my original vector. I'm going to call it as a R. This is my assisting vector. Let's call that as a V here. And this is how the R matrix to be vector will be rotated at. Okay, makes sense. You still with me? All right. So then again. So components we need to look at is, of course, this vector V, unit in a length. We need to take a look at this angle theta. And then that's it. That's basically all we need to know. And of course, we're going to compute the relation between the original and final configuration of the vector using these components, V and theta. That's what we're aiming for. Okay. So we need to play a lot of trigonometrics to make things to happen. So we need to find, a little bit about, how to compute this one here. This is what we are really aiming for. So we need to know where this getting started and where it ends. So a relation between the Q and the P. Let me make it clear to you. Okay, Q and a P. And moving from Q to the P, we're going to make two assisting vectors, the one that is called B1 and one that is called B2. Once you add it, B1, B2, you're going to get this one here, which is one that is called here delta R. That's what we're aiming for. Now, each vector, only information we need to know about each vector is what is its direction and what is its length. This is the information we need to know. And what follows is a very, very painful mathematics, which we're going to skip because it's almost 6 o'clock. So it's against the law if explaining that heavy mathematics this time of the day, because you guys probably will not sleep well if I do that this time of the day. I heard that if you drink coffee, having heavy mathematics after 5 o'clock, you don't sleep well. I don't know if this is really the case or not, but we'll see. We're going to go easy with this mathematics, but again, we're aiming for getting these two vectors, b1 and b2, and we can get it by this way. This is the b1 and b2. Each of them are getting like this. p1, we need to know the length. Again, it's coming from trigonometrics. So once we know each of these components, like how much is a radius of this circle here, and once we know the angle theta, this is how you can do the math. And then we need to know the direction. Direction have to be unit in length, so that's why we take a cross product of v and r dots, r bar, excuse me. And once we make a length, unit length out of this vector, this is what we're going to get. So this is how we can write the p1. Similarly, we can write the b2. And again, don't get stuck with the details because they are not important. Only thing important is this concept, how you can do this Grothendieck equation. Again, length, direction. Once you're combining everything together, you're going to get this one here. And then once you're putting these two vectors together, you can compute the delta r, something that we are aiming for. And delta r, when you take a look at it, how is the delta r? We can actually take this r vector away from the equation. What's going to be left is going to be Grothendieck equation. This one here, this shows the relation between the original and final vector. Original, final vector. The one thing that I did not explain here is that this cross product of two vectors can be dealt differently than using the cross product. I don't know if you ever heard about skew symmetric matrices. Have you ever heard about that? Okay, so if you have a cross product of A multiplied by, cross product by B, you can explain this in such a way that you can build the skew symmetric matrix from A and multiply that by B. How that goes? Goes such the way that it's explained here. You just take a matrix here, the one that is formed to be a skew symmetric form. You take each of these components and you just locate these components to matrix that is called a skew symmetric matrix. Skew symmetric matrix is something where the diagonal terms are equal to 0. Enough diagonal terms are asymmetric. So the first component, A, goes here in minus sign, and it goes here with a plus sign. Then the second component goes here in the plus sign, here in the minus sign. Third component goes here in the minus sign, here in the plus sign. This is forming skew symmetric form. Why? Because then we can get rid of this painful cross product. We can use just a little bit more pleasant notations, which is based on these skew symmetric notations. Content-wise, no difference whatsoever. Now, when we're using these notations of skew symmetric vectors, rotation matrix look like this. And now we have 4 parameters. And why we have 4 parameters? Because first of all, we have this vector v that consists of 3 components. And then we have this angle theta, 3 components. Excuse me, these 3 components here, plus 1, 4 components in total. 4 components in total. So how this is possible? Is it this something that is off? Because is it the case that body can rotate in 4 different ways? No, it cannot. That's against the physics. There is something that relates these parameters together. Something that relates these parameters together is the fact that this vector v was, what did I say? I said that there's a special condition. What was that? Correct. I got the friend. I have a friend in this class. Can we be friends? Fantastic, really nice, because it's exactly the case. It's a unit in the length. So there's a constraint equation involved. So we do have 4 parameters, but then we have one constraint equation. So the body can rotate in 3 different ways. Nice. Super. All right, so 3 parameters, 3 variables here, 1 variable here, 4 variables in total. But because of this, this vector here is a unit in length, we're going to get the one constraint, and one constraint look like this. So when you take a v first component power 2, second component power 2, third component power 2, it have to be equal to 1, because otherwise not unit in length. And this is a one constraint. But that's fine, because in the multibody system dynamics, we used to do with the constraints. So this is just one additional constraint that comes along, so not that big of a problem. So that's how this Rodriguez equation works. And I'm going to have this last in-class quiz, and then we will be off. My last in-class quiz is in Rodriguez equation. Rotation is described by 4 parameters: v1, v2, v3, and angle theta. 4 parameters are coupled because angle theta is small. Vector v is unit in a length. We are assuming the body to be rigid. The parameters are not coupled because body can rotate in 4 different ways. Okay, let me put this on. And once you guys are done with this in-class quiz, where is it now? Here. This one. Then you can go. Are you going to sleep well because of the involving mathematics? Hard to know. Hard to know. So what are the other, hey, by the way, have you guys already applied the summer positions, summer job positions? You have? Because you should. This is the time to do that. Because some of the, I think if not all the places are open at the moment, and they're going to close sometimes in January. Some of them are closing already mid-January, so make sure you apply. So can you give me a promise? So each one of you have to submit at least 50 applications. 50 applications. Why not? You know, it's doable easily, because with your good friend of ChatGPT, you are, you know, every time you are, because what happens is that you are creating this later that say, oh my God, this is a company is fantastic, and I've been studying your values and everything, and my values are in the line of your values, and then the ChatGPT explain how they're in a line, and then this is the way that you make these companies to be impressed. Okay? Is 50 applications too little or too much? How many you need to apply usually? Quite a few. Okay, but make sure you apply, because this is the time to do so. And you can use me as a reference if you want. Sure. And sometimes they call me in a companies, often they don't. They don't. Okay, but here, back to this business, so we got roughly the same number of answers than in the previous case. And correct answer is V is unit in the length. V is unit in the length. Other options, angle theta is small. That's not the case. It can be any value it wants. We are assuming body to be rigid. That's not the case here. Okay. All right, guys. Let's close this technically difficult day today. And I'm going to see you on Monday at 10 o'clock, 10:15. But not this place. It was something like 733 something. Take it easy.